I want to welcome you to another statistical learning class. Before I get started today, I think I'm going to say I've already updated um group group project presentation. I need you to check. I think I received some feedbacks from students, and I like listening to feedbacks. So because of that, I'm actually going to allow you to form your group. So make sure you check the announcement section for updates. Um, we have our exam coming up on Monday. Of course, you know that. And I've already uploaded the midterm two practice questions. You can check the model. And not only that, I also attach, the particular areas in the lecture notes that you need to review. So I also uploaded that. Let me see if I can quickly show you. Give me 1 second. Let me see. Should I share the model? Okay. I'm gonna go all the way. Now take a look at this. So, uh, this one is a practice question, and this is the particular area in the notes that you need to focus on. So, right now, starting a new chapter. Of course, what I'm going to start right now will not feature in midterm two. Okay. Now I want to start classification. Okay. At times, we may want to, classify the response variable into two or more classes. And how do we do that? I said two categories or more. Okay. And this is more or less like predicting our response variable. The response variable here is qualitative. It's qualitative, not quantitative. Okay. So if I have information about predator, can I make a prediction of, where, can I classify, okay, that particular, observation into an appropriate class? For instance, there's so many examples here that we can actually use. So in order for us to do that, we need what I call classifier. Okay. The same way doctors in hospital, we base on the information about what the predator value is, they can make a prediction about whether the person has disease or not. Okay, even in banks, where customers may approach a bank for a loan, okay, and the bank want to classify the customer into whether it's going to default or not. So we need a classifier to be able to do that. I think I gave a lot of examples here. Predicting the outcome of a future basketball game. Of course, we all know whether it's either they win or they lose. Okay, I remember one time that I was watching, is it Timberwolves? Has anybody watched Timberwolves before? I think that is Minnesota basketball. Okay, yeah, I think I watched them before. Or watching, there's another interesting one, Golden State Warrior. Yeah, there's one guy that normally make 3 point. He can stand from far and what is the name of it? Oh, is it Stephen Curry? Yeah. Okay. So based on their placements, when you have a team based on the way they are placed in the league, can we have a way to predict the probability they're going to win or not? We could base our prediction on one predator. It could be more than one predator, maybe based on the age of the players, the years of experience of the coach, because All of those factors could determine whether they're going to win or not. I give another example. We want to predict if a student will enroll in a summer school, okay? And this is a function of family income, numbers of siblings, GPA, and so on, like that. So this is a classification issue. Now, here I said, since the goal of a classifier is to assign a category, you know what we want to do? A classifier will assign a class or category to each observation. So which means initially we do not know where they are classified, but based on what we know about the values of the predator, I'll be able to classify them. Okay. And that was why I said the way this assignment is performed is by predicting the probability of falling in each of the category. Because we live in a world that is probabilistic in nature, if we want to classify, okay, you are likely going to be in a particular group if we realize the probability of being in that very group is very high. You are not likely going to be in a particular group if the probability is very, very small. So which means we're actually going to base that on probability. And of course, we've done something like that before, like using logistic regression. I remember when I was walking you through the binary logistic regression. With the binary logistic regression, don't forget, we have two, it's more or less like we have two classes, okay, binary, okay, two groups that we want to classify. And of course, we have multinomial, where we have more than two groups, and we have the proportional or where the ranking is involved. Okay. And I also talk about the generalized additive model. I remember when we were working with beyond linearity. Let me tell you something. We just concluded beyond linearity, the parametric and the non-parametric. The response variable may not necessarily be continuous. Using all of that, I can have a continuous. I can even have a categorical. Then I can have counts. So which means the same way that I can have linearity that has to do with continuous, that has to do with categorical, that has to do with count, we can also have that for non-linearity. Even though what I walk you through the other time, I only focus on continuous, where we are trying to fit a befitting model that will capture relationship between wage, you remember, between wage and age. Okay, this is X, this is Y. Here we are considering continuous. Okay, we can also do the same for categorical. Okay, we can have a logistic regression that is non-linear. That's what I mean. We can have a Poisson regression that is also non-linear. You remember we have had Poisson regression that is linear. Why do I say Poisson regression linear? Poisson regression linear log lambda equal, because the log lambda is linearly related to this. Okay. And if I'm considering logistic regression with non-linear, okay, I'm actually saying the logit, okay, the logit is linearly related. We can also have situation where we're not going to have linear combination, even though the response variable is categorical, is a count, and so on like that. And of course, under the under the generalized additive model is when we're now focusing on more than one predator. The other time I was talking about effect of age on wage. I can add another one, experience of workers and so on like that. And what the generalized additive model is going to do, instead of considering the linear combination, okay, what we're going to have is going to be f of x1, f of x2, and so on like that. So what I'm trying to say, we can also use that even if Y is not continuous, if Y is categorical, generalized additive model can also be used as a classifier. Does that make sense? Okay, we've had different kind of models, and that's why I said indeed, if you think about it, we have already studied at least 3 classifiers, even if we did not really call them classifier. They are classifier. So they are classifier if and only if the response variable has categories. Does that make sense? So if response variable have categories, whether they actually going to have a linear they could have a linear combination, they could have a non-linear combination. Now, we now want to consider different kind of classifiers. Now, what I'm going to walk you through today, I'm going to walk you through the Bayes classifier and the KNN classifiers. Okay? And of course, on Monday, because, sorry, um, on Friday, I'm actually going to work on the other classifiers. Of course, I'm going to dedicate tomorrow, sorry, Wednesday for midterm 2 practice questions that I uploaded. So this material now, I'm going to walk you through this material today and on Friday. Does that make sense? Why on Wednesday is going to be, the focus is going to be on the midterm 2 practice. So we're going to discuss 4 different kind of classifiers: the Bayes classifier, the KNN, the linear discriminant analysis, and quadratic discriminant analysis. But in this lecture, we're only going to focus on Bayes classifier and KNN classifiers. Why on Friday, then we're going to talk about linear discriminant analysis and quadratic discriminant analysis. I want to welcome you to Bayes classifier. Now, why is it called a Bayes classifier? It's called a Bayes classifier because we're actually going to use the idea of Reverend Thomas Bayes 1759. Okay, we're going to use the idea of a Bayes rule. And I need you to pay attention. When you talk about Bayes, in a Bayes theorem, we actually going to consider um, prior probability and posterior probability. Okay, so give me 1 second. We're going to talk about prior. Okay, so what do we mean by prior? What do we mean by posterior? So prior and posterior. So prior probability is the probability of the state of nature before collecting data, before you collect data at all. Okay, what is the probability of state of nature? Maybe somebody walk into your bank to get a loan, and you have not really, maybe you don't have information about X, the predator. You don't have information about the person's income. You don't have information about the guy history, but maybe probably looking at the person, the way the person look, or so, I don't know. You just have it in your mind that probably it's not likely going to pay back, or it's going to pay back. So that's a prior. So which means you've not collected data at all. But if you now collect data and you combine with a prior, then that becomes posterior. Now, if you take a look at the under the Bayes classifier, I said we want to classify observation into 2 or more groups. You can see Q greater or equal to 2 into 2 or more groups, because we believe the observation Y, okay, can be classified, belong to a particular group. And that was why I said it takes on Q distinct values. Okay, now if I let Q or pi Q prime be the overall prior probability, when I say prior probability, that is a probability, okay, of the state of nature before data collection. I've not collected data, or I've not collected a predator. I don't have any predator value about a person. Okay, and that a randomly chosen observation come from the cute class. That is why it's called pi q. Okay, now let f of s be equal to this. Now, take a look at this now. Data is now involved. Data is involved when there is x. X is a predator. Maybe I know the income of the person. So the f of x q means the probability that, oh, after knowing the income of this person, okay, I can now classify this person to a class. And that is what we mean. I said denote the density function of x, okay, for an observation that belongs to a class q. So the density function of s is more going to be like the frequency, okay, like the percentage, okay, we know or that, and which actually tell us the probability that an observation is actually coming from q. Okay, the probability that observation coming from class q has a particular value for predator. Does that make sense? And that's what we mean. Now, the x that we're talking about, the predator that we're talking about, could be one dimensional, could be multi-dimensional. So which means I could have one predator and I could have more than one predator. That's what it means. Okay, now that's why you see more than one predator, x1, x2 up to xp. Now, the idea of a Bayes theorem is actually going to be applied. Now, if you the one we know first is this guy here, the probability of y equal to q. Okay, the probability of y equal to q, you can see y equal to q. There is no any predator x, which means I've not collected data, and that's a prior. That is the probability of the state of nature before collecting data at all. That's a prior probability. So I'm going to denote that as a, pi q prime. Now, when you take a look at this guy, oh my God, that is what we call a likelihood. Likelihood. So the probability density function, okay, that's a likelihood. The probability of s equal to s given that y equal to q, that's a likelihood. Now, what do you think I'm doing right now? I'm combining the likelihood with a prior. Combining the likelihood with a prior, what I have in the denominator. This is synonymous with you having probability of B given A equal probability of A given B multiplied by probability of B. And here you have probability of A, and the probability of A is a total probability. It's a sum of what you have here. Okay, where just J start from 1 to whatever that we call a Bayes theorem. So what I'm trying to say now, the 1 in the denominator is just to normalize, is a total here. So the py equal to a, I call that pi q prime, and this guy is a density function. Then you're actually going to see that the numerator here, the denominator is just the sum of the numerator. Now, everything here is what I'm going to call that pi q. Pi q is for posterior, and pi q prime is for prior. So the idea is that if I start with a prior probability, if I have a prior belief about something, and the moment information is available, that my prior knowledge can be updated, okay, with the evidence. If somebody is accused of committing a crime in a court of law, before the court of law, the person will be assumed to be innocent until proven guilty, right? So when new information, there's possibility. When new information is available, when new evidence is available, there's possibility that the person they maybe maybe charged more, or they're going to say, okay, we don't have a case anymore, we have new evidence, stuff like that. So this is what we call Bayes classifier. So the probability pi q, which is the posterior probability, okay, is the one that we that we actually correspond to the base classifier that we so that is that. But let me tell you this. Somebody can ask, what is the difference between just having a prior information and a posterior information? Prior information, you do not have you know, information about predator in the prior. Okay, you do not have information about predator, but the posterior is a combination of a prior and the likelihood. The likelihood is, no, I have information about predator, and that was what I said here. If you take a look at what I said here, I said, what is the advantage of using a pi q? The pi q here stands for posterior. Why pi q prime stand for prior? And I said we can include information associated with predator. Does that make sense? So it could be one predator or more than one predator. Is there any question at this time? Any question? Okay. Now, if there's no question, I'm actually going to move to how an example. For instance, how do I use a base classifier if I have observations that are expected to come from two categories? Now, with the category Q equal to 2, how do I use a base classifier? If I want to use a base classifier, then I will need to, four of us, have a threshold. Now, because I know the total area under a curve is 1, then I can use the idea of a 0.5. Okay, so I'm going to actually talk about the one that fall below 0.5 and those that fall above 0.5. Okay, to be able to classify. That's what I'm saying here. You know, I said if you take a look at this now, that's a posterior, right? If you go back, come back here, what do you see? The probability of a y equal to q, okay? Y, an observation being classified into q class, given that I've observed the predator. Does that make sense? So right here now, this guy here, I'm actually using for an observation to be classified into group 1, then the probability, the posterior probability must be greater or equal to 0.5. So definitely opposite this, then it should be in the other class. If it is less than 0.5, it should be in the other class. And that was why I said, and class 0 otherwise. Why do I say class 0 otherwise? No, maybe right here, what I'm trying to say right here is that, you know, our y is dichotomous. Y can be 0 or y can be 1. Y equal to 0 is in class 0, y equal to 1 is in class 1. So right now, if you take a look at what I have here, is the probability that is going to be classified in class 1, given that I've observed the predator. It's actually greater or equal to 0.5. Okay, so, and what we normally focus on, so which means we're actually favoring greater or equal to 0.5, then for an object to be classified into a particular, then we're actually seeking the largest value of that. For an object to be classified into a class Q, okay, then we actually seeking the largest value of the posterior, because we said something here that it has to be greater than 0.5 to be in a class 1, to be in a particular class of interest. Then we are seeking a situation where the posterior is actually going to be the largest. Does that make sense? The probability is going to be the largest. Now we can demonstrate that. Okay. Now, and as I said in the plot below, we consider a simulated data set with 1,000 training observations, because let me tell you this, the way we can actually evaluate the performance of a classifier is when we actually conduct an experiment where we have some training data point and we have a test. We already know the class of the observations in the test. We can actually ask our classifier to actually make a prediction. Okay. Now, at the end of the day, you'll be able to compare whether the classifier has done a great job or not. Now, what I actually want to do, I need you to pay attention right now. What I need you to do, I said, if we have 1,020 observations and two classes characterized by orange and blue color, okay, we have 1,000 and they are actually distinguished by two different colors. I'm using color now as a class. Okay. Now I said the purple dash curve correspond to the Bayes decision boundary. That must be a boundary. You know, the other time I put as 0.5. Then the point where the Bayes classifier assume value 0.5. That is the boundary. Now, hence, all the points, you're actually going to have a point on the left of the boundary. You're going to have a point on the right of the boundary. And I need you to pay attention and take a look at this. Now, the Bayes decision boundary, you can see it's like a curve, right? Let me tell you this. The Bayes decision boundary, okay, may be non-linear in nature, may be linear in nature. Does that make sense? By the time we're dealing with a linear linear discriminant analysis and a quadratic discriminant analysis, you're actually going to see that. So right now, you can see that we got some kind of misclassification. Okay, in this category, can you see some colors of this here mix? Can you see that? And you can see some blue here too. Okay, that is telling you there's no perfect classifier. There's always going to be what? There's always going to be error of misclassification, error due to misclassification. We know we acknowledge the fact that there's always going to be error, but if the error can be minimized, if the error can be very small. So if you take a look at, you remember the other time when we are focusing on a prediction problem, we use mean-square error, right? But when you are focusing on a classification problem, we talk about the test error rate. We discussed that earlier in the semester. So as you can, is there anyone who doesn't understand this? You've seen the Bayes decision boundary. That is a Bayes decision boundary. Okay. And we've already done the classifier here. Y equal to 1, Y equal to 0. Okay. That is the labeling. Okay. To indicate that we got two categories. Now, I've talked about there's always going to be error rates. And I said the Bayes classifier produces the lowest possible test error and which corresponds to this. Okay, which corresponds to that. So the Bayes error rate is going to be 1 minus the expected value of the maximum. Because you know why? We are seeking the maximum posterior value. There's going to be so many of them. And that is why you can see here the average. You see the average? So 1 minus that. And you know the average of a pie, okay, is definitely going to be a pie. If you remember Bernoulli, okay, Bernoulli distribution. Okay, if y follow Bernoulli, the expected value of y is p. Okay, the mean is the probability of success. And that's exactly what you're saying. But there's something that is going to be an issue here. I said, unfortunately, since the probability pi q are unknown in practice, let me tell you this, posterior are unknown in practice because, you know, you remember the other time we have a pi q prime, that's a prior. There's possibility we know the prior because we can even know the prior before collection of data. But without you collecting data, there's no way you're going to get posterior because the posterior is a combination of a prior and the likelihood. And that was why I said, you know, unfortunately, since the probability, okay, probabilities, pi q are unknown in practice. If they are unknown in practice, there's no way you'll be able to classify. There's no way you're actually going to get an error rate associated with that classifier. And that was why I said we cannot compute the Bayes classifier and the importance of properly estimating. Well, we can estimate. Does that make sense? We can estimate that. And one of the ways. we can estimate that, is to go and use a KNN neighbor. Okay? That is one of the way, which is going to take us to KN nearest neighbors. You can see statistics like a story, right? So we actually want to use K nearest neighbors, okay, in this regard. Now I'm going to tell you how K nearest neighbors actually work. You remember the other time when we're dealing with the beyond linearity, when we were talking about local polynomials and kernel smoothing. You know, the kernel smoothing actually use, they pay more attention to a neighborhood where they give a huge weight to the response variable that are in the neighborhood of the predator value under consideration. We're also going to do the same here. Now the K nearest neighbor, what we normally this approach we requires that we determine ahead of time what is the numbers of neighbors we want to use. The neighbors choosing must not be too small and must not be too large. Okay, if it is too small, there's likely going to be a problem of high variance. Okay, the model, the classifier may do well on the training and may perform poorly on the unseen. And if it is too large, it could over smooth the boundary. I show you the Bayes decision boundary, right? We don't want situation where that boundary is going to be over smooth. When it over smooth, it means there's going to be a problem of high bias, which means you are oversimplifying the model. Okay, so the way the KNS neighbor work uh, is that you're going to choose the numbers of neighbors ahead, and after choosing the numbers of neighbors, you know what you're going to do? You're now going to find a distance. Let me do that here, and so like I said, you're choosing the numbers of neighbors. Okay, K has to be choosing. That is the step number one. Number two, you compute the distance between the test point and all training points. And if I want to compute the distance, okay, I have different metrics of evaluation for distance in literature. You can use Euclidean, you can use Manhattan, you can use Minkowski. But here the popular one is Euclidean. Okay, Euclidean is well known in literature, where I'm actually going to find the square root of x2 minus x1 squared plus y2 minus y1 squared, and after that, what I'm going to do is to identify um you know the um the nearest neighbors, in my training data, and after that, I will now need to identify the highest posterior. I'm going to give you an example on how that can be done. Give me 1 second. I quickly want you to see. Okay, I think I'm going to write it down here because um let me see if I stop this. Okay, now I see the board. Okay, I think I'll be able to see the board. Okay. I want you to see how how the KNN neighbor is actually going to help. Is going to help out. Let's say, for instance, I have 6 apples. Okay, and those apples, some of them have this color, the other ones have that color, but I don't see them. Maybe I close my eyes, and they say, okay, I should eat the apple. Maybe I know the weight of the apple and I know the sweetness. But you know what I want to do? I want to identify the color of the apple that I've eaten. Does that make sense? Okay, so I want to show you how the KNN neighbor is actually going to work. Now, let me tell you this. Let's say fruit, okay, weight, and sweetness. Sweetness. Okay, A1, A2, A3, O1, O2, O3. What this is telling me now? Okay, uh, I have A, O. They've already been classified. Okay, but I don't know them. I just want to make a prediction. Now I know the weights. 180 for this, 170, 140, 200, 210, 190. Okay, and the sweetness 8, 7, 9, 5, 4, 5. Okay, label A, A, O, O. Let me see. Yeah, yeah. So A, O. Now I do not have access to this, but the only thing I know, X1, X2. Okay. Now, based on this information, this is, if I'm using this as a training, okay, based on this, and I have a new apple that is coming in, okay, based on this information, I have a new apple that is coming in, and the weight of the apple is 180, the sweetness is 6.5, and the question say, what is the fruit type? Okay, what is a fruit type? Okay, you know, let me just say this. Let me say we have different kind of fruit, apple and orange. Let's say this one, apple. Okay, this orange. Okay, and let me tell you this. Um, I'm not gonna eat because if I eat, I will know the difference between apple and the orange. I'm not eating this time around. Okay, the example that I was citing before is maybe they are all the same apples, and I want to distinguish by color. But right now, apple and orange. Okay, now maybe the only information that I know is it has a weight. That fruit has a weight 180 and the sweetness is 6.5. Then what type of fruit is this? Is it apple or orange? That makes sense? Then we want to classify. Now, if you want to classify, the very first thing you need to do is you need to decide on the numbers of neighbors, which we call K. Okay. Now, if I look at this data set and I choose K to be 3, okay, let's say I choose K to be equal to 3. The first step in KNN neighbors is to identify the numbers of neighbors. And after that, you now need to find the equilibrium distance between the training, okay, between the test. Like right now, this is more or less like a test. This one here, that's a test data. And the training, I have to compute the equilibrium distance. Now, if I want to compute the equilibrium distance, let me see. Of course, we all know that is the formula we're actually going to use. Now, what is going to happen is this. Uh, you actually, I'm going to start subtracting. Okay, I'm going to start subtracting. What am I going to subtract? You know, the weight 180. So this is what you actually gonna see me writing. Okay. Is there anyone who is not clear with how we use the equilibrium distance? Or what we are just doing, you were subtracting the test point, okay, from that. Okay. You can see 180, okay, minus that. You can see what we're doing. Wait a minute. I think the first one here should be 150. Should be 150. Yeah, 150. This should be 150. So because 180 minus that, 6.5 minus that, 180 minus that. So it's going to continue. Now, you know, before we start, we choose K to be 3, right? Now, let us now go to what we compute. Okay, what as the nearest one? Okay, so you know we said K equal to 3 when we start this, this, and this, right? Because we've already chosen K to be equal to 3. Now, in choosing K to be equal to 3 now, so what does this correspond to? Output 2, right? What does this correspond to? 1, 2, 3, 4. Okay, the 6.5, sorry, the 5 one. Orange, right? Orange, orange. Then what does the last one correspond to? Orange. What has happened now? It means out of the 3, 2 out of 3 is for orange, 1 out of 3 is for apple. Do you see that? So 2 out of 3 is for orange, okay? And you know, I told you the other time, the weight now, so the 2 out of 3. So what we are actually doing here is more or less like using the information here to be able to decide on what we have. So we are actually saying that looking into what we have, you know, the probability of being in an orange class is 2 over 3, and B in the other one is 1 over 3. Okay, so I'm actually, and that was why, like I said, we have one for apple and two for oranges. Okay. Then can somebody tell me how, where can we classify the observation? Where? Is it going to be orange or apple? Eh? Can somebody tell me for extra credit and you tell me with reason? Where are we classifying the observation? Is it going to be orange or is it going to be classified as apple? And if it is orange or apple, why? Go ahead. Which means that's a higher. We said we want to maximize that time, right? Okay, send me a message for extra credit. Thank you for sharing that. Now I quickly going to move. 1 second. Okay, so that is the way that guy walk. Okay, I gave an example here. Okay, take a look at this. This is what we're trying to say. Okay, this is a different one. Situation where we have blue, but this is just telling you sensitivity of K, the numbers of neighbors choosing. It must not be too small. It must not be too high. But how can we optimally estimate that? We can use cross validation. Does that make sense? So you can see the probability of blue is 2 over 3 when K equal to 3, and it is 2 over 5 when K equal to 5. So different values of K will give you different probability. Okay. Now I said, so, if you take a look at this, I said, for instance, the plot below, we compare the performance of KNN with K equal to 1, K equal to 10, and K equal to 100 for the same simulated data described above. So if you take a look at this is when K equal to 1, when K equal to 10, and when K equal to 100. But what I can observe, when K equal to 1 here, I'm seeing the fluctuations. You see the curve. This is not smooth. And high variance here will lead to, this is will lead to sit over fitness. This is going to lead to over fitness. But this one is going to, even though, oh, this is a very fine smooth, but this over smooth. Okay, this is going to have high bias, even though low variance. This is going to oversimplify. Okay, but the K equal to 10 is like something that is likely going to balance between the bias and the variance. So how we determine that? We can use cross validation. I said something here. So how does K impact the flexibility of the model? How would you expect the training error rate and the test error rate to change when K increases? There's something that I really want to talk about. I said when K increases, the training error, when K increases, the training error rate increases. Okay, the training error rate. Okay, you know when training error rate increases, but if the test error rate, the most important thing is the test error rate. Even the training error rate may be very small and the test error rate is high. We don't want that. Okay, we don't really want that at all. And here I said K increases, then the decision boundary becomes smoother. Okay, if you take a look at this, it is smooth because K is large. But when it's over smooth, you know what is going to happen? When it's over smooth, okay, when it is over smooth, is going to, it may not capture the trend in data. Over smoothness need oversimplification of relationship. When you simplify relationship and the relationships of, oh my God, my time is up. That's 11. My time is up. I'm going to continue from here. Next time, I'm going to continue from there next time. And that next time is actually going to be on Friday, because on Wednesday, I'm going to walk you through midterm 2 practice questions. I need you to be around on Wednesday for that. Make sure you all stay safe and have a lovely day. Bye for now, everyone.